The IPERION IHS Heritage Macromolecular Lab is one of the Slovenian E-RIHS facilities and offers insight into macromolecular heritage materials and their interactions with the environment. By macromolecular materials we mean, for example, paper, silk, parchment, leather, as well as characterization of complex organic paint systems from complex pigments such as synthetic organic pigments and inks, traditional organic pigments and dyes, to complex binding media. IPERION IHS Heritage Macromolecular Lab represents joint excellence of researchers from the Research Institute of the Institute for the Protection of Cultural Heritage of Slovenia and Faculty for Chemistry and Chemical Technology of the University of Ljubljana. The uniqueness of the access is in the combination of analytical techniques and modeling approaches and understanding of the materials themselves, which offers full characterization and interpretation of natural and synthetic polymers constituting cultural heritage objects.
Proteins are natural polymers that are often present in cultural heritage objects, either in solidly proteinaceous materials such as feathers, fur, leather, parchment, or in process form such as adhesive, protective coatings, and binding media. Their investigation can be challenging due to low concentrations in solid matrices such as paints, presence of other organic materials derived from different animal or plant sources, previous conservation treatments, and similar. Furthermore, they easily undergo alterations such as fragmentation, alteration of amino acids such as oxidation, hydrolysis, deamination, and biodeterioration represents additional difficulties in their identification in works of art. When characterizing proteins, such as casein from milk, or albumin from egg white, or collagen from bone and skin, which are most abundant in art materials, traditional instrumental methods such as FTIR, pyrolysis GC, GCMS, HPLC may not be specific enough to give unambiguous results. This could be due to the required sample size, sample mixture, degradation, or the presence of microorganisms. For such samples, we believe that immunological analytical techniques of ELISA, or immunofluorescence microscopy, IFM, is essential for the determination of proteins in works of art. They offer high specificity of the interaction between the antibody and antigen, which enables us to distinguish between different types of proteins, as well as a lower limit of detection and increased sensitivity and accuracy. IFM can potentially also provide information on the spatial distribution of proteins within a sample, as well as their possible migration between layers within a sample. For example, between different pigment layers in a painting.
In addition to understanding the distribution of specific proteins using immunofluorescence microscopy, we also offer FTIR microimaging. FTIR imaging is useful to visualize the spatial distribution of other components such as binders, pigments, fillers, etc. in a sample. For example, the layered structure of paints in a cross-section of a sample can be imaged with 64 by 64 pixel resolution with full spectral information contained in a pixel. By integrating the characteristic FTIR bands of a sample component, we obtained images of its distribution in the examined sample. In a layered paint structure, we can thus image oils, resins, surfactants, inorganic pigments and fillers, as well as synthetic polymers.
Complex organic pigments and dyes are often oligomeric or polymeric materials and are essential coloring matters found both in traditional paint media or modern paints. Raman microscopy is an important tool to characterize paint cross-sections or surfaces of objects that are small enough to fit onto the XY stage of the Raman microscope. Our lab offers 2 Raman systems with 7 laser excitation lines, which is a unique system. The system allows us to characterize complex organic materials such as logwoodings, synthetic and traditional organic pigments and dyes, and similar. Dyes and lake pigments are difficult to analyze as they are often found in mixtures with other pigments where they are present in small amounts. While several analytical methods can be used for the analysis of dyes and lakes, many struggle with sample size, detection limit, selectivity, and other limitations. Surface-enhanced Raman spectroscopy has proved to be an extremely sensitive analytical technique suitable for this purpose. We have developed new and effective substrates for the source that enable us to characterize complex organic pigments and dyes in traditional paint media. By the end of the 19th century, synthetic organic pigments were gradually introduced into the market and started to replace inorganic and traditional organic pigments in artist media. In our laboratory, we developed a Raman database of over 100 synthetic organic pigments belonging to pigment classes of, for example, beta-naphthol pigment lakes, azo, diarylite, bisacetoacetarylite, phthalocyanine, azomethene metal complexes, isoindolinone, and many more. This gives us the ability to offer characterization of synthetic organic pigments in modern paints or colored plastic materials.
Although synthetic polymers are an important part of museum collections, few have conducted surveys to identify the types of material. Many exhibit specific conservation issues due to polymer-dependent degradation processes and may require specific conservation strategies. Reliable, non-invasive, on-site identification is therefore of high importance. In the Macromolecular Heritage Lab, we offer multivariate statistical tools for the identification of polymer type in plastic objects based on spectroscopic analysis. This makes use of our reference material collection that consists of several thousand objects, including more than 240 pre-characterized plastic objects. Based on optimally collected near-infrared spectra, we developed a variety of supervised and unsupervised methods of classification. We can successfully differentiate between a number of key polymers in collections, such as polystyrene, polyethylene, polypropylene, PVC, cellulose acetate, and ABS, with approximately 90% success. We also offer our expertise for similar data-rich projects, where advanced methods of statistical analysis could be useful.
Many synthetic macromolecular materials have complex compositions that may be important from the conservation point of view. For example, soft PVC objects may contain significant proportions of plasticizers that affect the way the objects degrade and can lead to surface stickiness. Their identity and content can be determined using gas chromatographic techniques. Fire retardants can be determined using liquid chromatography. Chain scission reactions may affect the mechanical properties of a material and can be studied by size exclusion chromatography. My work is looking at degradation of PVC using accelerated degradation experiments at different elevated temperatures and relative humidity. Based on these, I will develop a damage function which will help to shape preventive conservation guidelines. PVC degradation proceeds by elimination of hydrogen chloride, which leads to the formation of polyene sequences that can be recognized by characteristic yellowing. Additionally, degradation can become evident as increased brittleness and warping, which can result from plasticizer migration and loss. Similar approaches can be used for other synthetic and natural macromolecular materials.
Degradation of macromolecular materials, as well as many other materials, may lead to emissions of volatile compounds that can be harmful to the surrounding materials or to human health. For example, cellulose acetate, polyurethane, and polyacrylate emit acetic acid. At low concentrations, this can cause damage to other objects placed nearby, such as corrosion of non-noble metals, particularly lead, or degradation of carbonaceous materials. The Macromolecular Heritage Lab offers several methods to determine such emissions, their quantity, and evaluate the associated risks. These are based on active sampling with sorbent tubes or passive sampling with samplers. Compounds, such as for example acetic acid or formaldehyde, are determined with liquid or gas chromatography. We also offer testing in setups with defined temperature and humidity, which is useful for emissions that are a consequence of degradation of cellulose acetate, for example. I'd also like to add that many of these methods can be used to monitor pollutants in heritage sites, such as exhibition and storage spaces. We offer validated methods for determination of volatile acids and aldehydes, which are well known but insufficiently studied indoor pollutants.
The Heritage Macromolecular Lab, part of the Slovenian node of E-RIHS, can offer a range of techniques and methods to study natural and synthetic macromolecular materials, such as accelerated degradation techniques under the combined influence of temperature, relative humidity, light and pollutants, methods to follow macromolecular decay, such as size excision chromatography or viscometry, methods to identify and characterize macromolecular materials, from non-destructive spectroscopic methods in combination with multivariate data analysis to microdestructive spectroscopic and chromatographic methods to determine composition and additives, methods to study gaseous emissions from macromolecular materials of significance to degradation studies or to preventive conservation, damage modeling for preventive conservation in collections such as library and archival materials or modern materials, methods to identify and characterize paints from complex pigments and inks to complex paint media. Please contact us in advance of submitting a proposal to discuss how our methods can be useful in your archival and library materials research, plastics in design and art collections, textile research, and traditional and modern paints research. Thank you.